Howdy. Okay, so welcome back. Um, Today we're going to be talking about enzymes, and we're going to be talking about this for a little bit. And this will also lead us into talking about antiviral drugs, because I know those have been in the news quite a bit, so we thought we should talk about that. Um, so, one thing that I wanted to let you know about um, was that there's a new assignment up on Blackboard, and that assignment is a paper. And the way that that is going to work is that I'm going to have you turn in pieces, bits of work for the paper before you turn in the actual paper, so it kind of gets people who might be liable to procrastinate to break this assignment up into little pieces. And so what you're going to see up on Blackboard is that I'm going to make an entry to turn this in. What I want you to do is pick a drug that is meaningful to you and then write it down and why you chose it. And then you're going to enter that Word document into Blackboard and turn it in there. And there's due dates and everything is up on the announcements and the assignments. So be checking those things on Blackboard. That's how I'm going to be contacting this stuff to you. All right. So now moving forward with our drug targets as enzymes. So enzymes are proteins. They're typically going to be soluble proteins in your body. Globular, that means they're structured proteins that are soluble in the cytoplasm. And they're going to act as a biological catalyst. So they act as the body's catalyst. So you know that there's tons and tons, millions of chemical reactions that are happening all the time in your body simultaneously. And the reason that all these reactions can happen is that enzymes are making them possible, so that reactions that wouldn't go for 10,000 years if it was just the reactants sitting in a solvent of water can happen in a matter of seconds or milliseconds when there's an enzyme acting as a catalyst. So the way that the enzymes do this is that they lower the activation energy of a reaction, and that's going to speed up the rate of the reaction. So the example that we're going to use for this is going to be, for the next couple of slides, is going to be lactate dehydrogenase. And what lactate does is it turns the reactant, pyruvic acid, there on the left, to the product, lactic acid, on the right. So this is happening when your body generates energy. It's a biological energetic phenomenon. It also happens, it's one of the things that happens when lactic acid builds up in your muscles, leading to soreness. So you're going to see a couple things if we're looking at this reaction. Number one, we see those arrows, right? There's an equilibrium arrow. So all enzymes have equilibrium arrows, and all enzyme reactions are equilibria. And we can get them to go forwards and reverse under certain conditions. And this is something that actually happens frequently in your body and in other living organisms. And if people can actually engineer enzymes to take advantage of this. And so this happens, for example, in the biofuel industry. And so that's something important to think about, is that these are equilibria that happen to get enzymes to function. Also, notice there that we have NADH. So we've talked about that before. That's our biological hydride source. And NADH is going to be turning lactic acid into NAD+. So the way that enzymes work is that they turn they lower the energy of the transition state. And so what they're doing is they're lowering the activation energy for the reaction. So if you look on the left there, the way that you might have seen this, say, in Gen Chem, is that a catalyst, which enzymes are, a normal chemical catalyst is going to take the difference between the transition state and the starting material, and it's going to decrease that. So it's going to make the hump on that graph lower. And that's the activation energy. And enzymes do not do anything to change the difference in energy between the starting material and product. That's delta G. In contrast, enzymatic catalysts are a little bit more complex. And what they do is they have a series of equilibria as the starting material transitions to a product. The way that it interacts with the enzyme is more complex, but overall it's still doing the same thing, where it's lowering the transition state energy and it's having zero effect on the relative energies of starting material and product. So delta G remains the same. It lowers the activation energy, which is going to change the rate of the reaction. So there's two factors that are going to contribute to delta G. And so here, delta G, that symbol is a double dagger. So delta G double dagger is the transition state. And what we have here is there's two factors. One of them is delta H double dagger, and that's the enthalpy. And so this is basically enzymes are going to make it easier enthalpically for bonds to break and form. And enzymes are going to reduce the entropy of the transition state by setting up individual atoms in molecules or molecules themselves so that bonds can be more easily broken and formed. So they make it favorable for molecules to be in the right shape for the critical bond breaking and forming reactions to happen. So everything that we're going to think about when we think about enzymes, we're thinking about length scales of angstroms. So that's the length scales of chemical bonds. That's the length scale we're going to be thinking on, and that's the reason that all of this works is the precision of orientation of these atoms at very small length scales. So the reason that enzymes work, they have many reasons that they work. And one of the reasons that they work is that they're providing a reaction surface. So this is the active site, so we're going to talk about that a lot. They provide a suitable environment for organic molecules to bind, whether it's the substrate or a drug, and that's that hydrophobic pocket. And so that's the active site is a hydrophobic pocket. They bring reactants physically together, and so this is going towards the geometry for bond forming, and position them correctly for a reaction. They weaken bonds in the reaction and reactants, so that's relating again to enthalpically bond breaking. Provides catalysts, so additional stronger, essentially, reagents in the reaction. Is they provide their own reagents that are stronger than anything found in the solvent. What I mean is they provide reagents that are not available in the water solvent of the reaction. So our body is mostly water. We can think of everything as floating around in a water solvent for this purpose on the length scale that we're thinking about things. And it provides nucleophilic groups. Again, it's providing additional reagents, and it stabilizes the transition state with intermolecular bonds. So that's bonds between the enzyme and the substrate form that stabilize the transition state. And so that's relating to both enthalpy and also the entropy, reducing the entropic cost of forming the transition state while increasing the enthalpic gain of forming the transition state. All right, so here, this is where I would have done board work in class. So I will have in the slides for you, there should be an embedded video at this point in the slides. I might instead, I'll probably actually do this as video 1 and links attached for the lecture, and you'll have to go back for the empty slide and fill it in. Yeah, I'll do that way. Making a note to self. Okay, so the enzyme active site is this hydrophobic cleft that accepts reactants and cofactors, and it contains these amino acids that are going to both bind and participate in the reaction. So we're going to talk about these separately. So first we're going to talk about binding the reactants. So we're only going to talk about substrates right now. We'll talk about cofactors later. And then we'll talk about how amino acids participate in the enzyme catalyzed reaction after that. Okay. So substrates bind with bonding forces, and so these are non-covalent interactions. So remember before how we were talking about how a drug binds a receptor, and we said that a drug binds a receptor through non-covalent interactions, and any one of those non-covalent interactions, if you just had one, they're kind of crappy bonds. And we remember we talked about them in Gen Chem, we considered them crappy bonds, weak bonds. But if we have a bunch of them happening at once, they all add up and form an additive effect, and they're really important. So these non-covalent interactions are again the reason that the enzyme binds its native substrate. And what happens is that when these bonds form, we're going to see that they actually induce a change in the enzyme and the substrate. So both things are going to change shape. All right, so our example now, again, is we're talking about lactate dehydrogenase. And what happens with lactate dehydrogenase is first it's going to bind that reactant. In this case, it's pyruvic acid. And then one of the things that we can think about is that when it binds pyruvic acid, if you look on the left, if we look at this molecule, pyruvic acid is a really simple molecule. And we can go through its groups and think about, even in the context of Lipinski's rules, for example, we know that it has H-bond, H-bonders, in this case, H-bond acceptors. We know that it has a charged group because it has that carboxylic acid. So you could either think of that as the charge localized on the one carbonyl, or you can think of it resonating between the two carbonyls. And it also has that CH3, so that has a Van der Waals group. So I already know, before I knew anything about the enzyme, what the possible binding modes are of pyruvic acid, what the potential is, whether or not that actually all those bonds that I have guessed could form actually form with the enzyme. That's something I'm going to have to figure out. But I know a priori, I know from just looking at the molecule what potential bonds could happen just through the nature of my substrate molecule itself. Okay, so here you're going to have to watch video 2, and I'll do the board work for this slide. Okay, so when we're talking about substrate binding, if the substrate just were to bind, something's got to happen right to the substrate for it to get turned into the product. And what's going to happen is that we need to turn the substrate into something that looks more like the transition state. So what happens is that the active site first is going to kind of alter its shape when that substrate binds, because what the active site wants to do is it wants to change the substrate somehow. It's going to change the shape of the substrate. And so it wants to attract the substrate there and keep the substrate bound, but then what it wants to do is make the substrate turn into something else, right? It wants to make the substrate turn into a product. And so that's what's going to happen in these next steps, is that that's what's known as that induced fit. And so what we're seeing is that the substrate binds, and then the active site of the enzyme, the whole enzyme, in fact, changes shape. So in our example here, we can think about this with pyruvic acid binding. And here you're going to have to go to video 3. And then we can talk about when pyruvic acid's bound, the general and acid-base catalysis. So general acid-base catalysis, there's, you're going to have to go to video 4 for this, so I won't go into it. Note to self. Okay, so now that you know about the difference between general and specific acid-base catalysis, we can use that mechanism to talk about how this works in enzymes. So for acid-base catalysis, one of the common acid-base catalysts is histidine. And so histidine, remember its side chain pKa is about around 6, right? So it can act as both an acid and a base at physiological pH, which is at 7.4. But remember, the thing that's, I would say, is that it's easily kind of ionizable. So it easily interacts with a proton, because you'll find that the actual pKa of an active site of an enzyme is a lot different than physiological pH, because of how all those amino acids are organized in the active site. They can do a lot of different chemistry because of how they're set up. So other acid-base catalysts are aspartate, glutamate, histidine, so these, and cysteine, and of course metal hydroxides. Metal ions play a huge part. These are either transition metals, or they're metals like calcium, for example. Zinc's another really common metal in a lot of enzymes. Manganese, magnesium. Some of the more common metals. And some of these enzymes, like for example aspartate, we can see that it's an acidic amino acid. We'll also see it acting as its conjugate base, and the same with glutamate. Histine, we already saw that it can act as an acid base, and cysteine, remember this is acidic, but it can also act as a nucleophile. So the other potential acids and bases can be things like occasionally something like asparagine, but this is where you're going to go to video 5. And then I'm going to show you something cool. All right. Also in the active site are nucleophilic residues. So nucleophilic residues, they can be things like serine, cysteine, threonine, tyrosine, and those are the main ones. Occasionally you get a lysine doing this too. So I would say lysine's in there. So here's serine acting as nucleophile, and we're going to talk a lot about serine. in this class. So what serine can do is that OH group can act, the side chain can act as a nucleophile. And what can happen is that it actually attacks a substrate and causes a substrate to leave. You form an enzyme substrate complex, and then water, the enzyme is doing this, the water's not just coming in. Water can then act to, water can then act to hydrolyze the product.